Hey guys, welcome back to my channel. For those of you who don't know me, my name is Thomas. I'm CTO at Morpher.com and I'm the creator of Ethereum blockchain video courses. You might have seen them on Udemy or on similar platforms. Now in this video, I want to talk about smart contract upgrades and proxy patterns, as the title suggests, and I hope that's the reason why you're here today. I made sure to tag everything according to the time codes, so you can skip around if you want to, if you're just interested in one of the patterns, or if you don't like my babbling at some point, just make sure you just skip to the one that interests you. So what are we doing in this video? I want to start by separating logic and storage and walk you through the most simplistic of all patterns that are there, and then go gradually over what emerged over the years. So I want to start with the eternal storage pattern. Then I want to go over to the proxies, the very first proxy from Nick Johnson, and then gradually over to what OpenZeppelin is doing with the unstructured storage, and then the diamond storage that came out now. And then I want to do something which is called Metamorphosis smart contracts, where you basically redeploy a smart contract on the same address but with a different bytecode. There's a lot of content to cover, and if at some point you disagree with what I'm saying, or if there's anything to add, make sure to leave a comment below or connect with me on LinkedIn. Go to Vienna, have a coffee with me. Enough from my side for the intro. I would say, let's go. Now I'm here in Remix and I already have prepared a smart contract that is our problem child. So let's define what we are actually having a problem with. Now the problem with this smart contract is the following. When you're going to deploy this and you overwrite this storage variable and you find a bug, and you redeploy it, you not only lose storage, but you also lose the address this smart contract is running on. Let me show you how this works. I've compiled it, I've enabled auto compile, so it automatically compiles. Going to deploy the lost storage smart contract here. My address is 0 initially. If you're going to overwrite this with some address, then it's going to have something in the storage variable. And now if I find a bug and you redeploy the smart contract, not only is your storage again empty, but you also have a different address this smart contract runs under. And that is a perfectly normal behavior. It's actually wanted behavior, but there are ways around that. And that is what we are going to discuss now. The different ways that we can have to either keep storage, lose address, keep storage, keep address, and lose storage. So those are the things that I'm going to tackle. Now, before we are actually going into the first pattern with this, which is the eternal storage pattern, let me give you a brief overview of what you're going to get into or get out of watching the whole thing. Now, the first one is we're going to talk about the eternal storage pattern because it's, I think, the easiest one to understand. You will lose address, but you will keep storage. So we're separating logic from storage here. Then we're talking about proxies. Proxies are ideal if you want to keep the address that your users are interacting with, and potentially either keep storage or lose storage. That depends on you. Normally it's keeping the storage. Then we are talking about the diamond standard. And at the very last, we are going to talk about metamorphic smart contracts, which is kind of a special thing with the create2 keyword, and where you can deploy a smart contract on a specific address, then erase it, and then redeploy a smart contract, but with a different logic on the same address, which is kind of a dangerous thing. Becomes more and more hard to audit if you want to have it run through auditors. All right, let's get started with the first one, with the eternal storage without a proxy. Great, let's have a look at what we can do if we are going to separate logic from storage. And as you can see here in Remix, I already have a second file, eternal storage, and I'm going to walk you through the whole thing in a second. But first, let me talk about how it is meant to be. Now, when we're talking about separating storage from logic, then we are usually having a storage smart contract that is purely storing the values and doesn't have a lot of logic. And then we're having a logic smart contract. In this case, we have a ballot smart contract, which is a simplified version of a voting system that basically lets you vote on something. It has an additional layer here, which is the ballot lib, which is meant to take directly the logic from the eternal storage pattern from Eleanor Dimitrova And you can see it in her example in her blog. The smart contract is taken from her example in her blog and a little bit simplified. Her example has string storage, address storage, byte storage, and int storage as well. I just took out 2 examples of this and reduced it to the absolute minimum to make an example of how the eternal storage works, because I found the simplified version is better to run for understanding. And then she decouples logic and the interface that the user sees into a library and an actual smart contract that runs somewhere. Now you can even make it more simple. And the way this is done is usually by directly having the variables that you need in your logic smart contract in a storage smart contract and not any logic there. So if you, for example, have a token balance, then you have a mapping of token balance in your storage smart contract, and the simple interface would let only your logic smart contract interact with that balance. You update the logic smart contract, you point it again back to the storage smart contract, and you don't lose your storage. But I thought, why not just run with this a little bit more elaborate example where there's a library involved. So let's get started with actually running that. All right, the first thing that we have to deploy is the eternal storage, and that will remain on its address. That is the important part. And then we can deploy our ballot smart contract over here, which takes in the constructor 1 argument, which is the eternal storage. So I copied this one over here, pasted it here, and deploy it. Now you can see, well, we can interact with the smart contract, we can vote, and the votes will go up. The way this works is in our ballot smart contract, we are using the ballot lib for address. And then we say our eternal storage is running on the specific address. And because we are using our ballot lib for address, we can say any address dot these functions that we have defined in our library. And in our library, we say then the eternal storage running under this eternal storage address is going to set a uint, and in this case our eternal storage is taking bytes 32 as a key value store, the key for the key value store, and in this case we are saying our Kazak hash of votes is going to be our key, and it saves the vote count somewhere. And the same is for the get uint value, it gets the vote count back. It is a fairly standard key value store, there is nothing specifically outstanding over here. If we are going to vote, then it is going to set vote count. If you're going to get the number of votes, then it's going to get number of votes and getting the uint value over here. So that is standard. Now, what if we are finding a bug and we want to upgrade this smart contract? So let me upgrade the smart contract and walk you through the changes so that a user can only vote 1 time and not more. Because right now you can vote as many times as you want. That's maybe not the behavior that you want to have in a voting smart contract. All right, I've updated the smart contract, and what I've done is I have added in the vote functionality. I require that if the user has voted, well, it must be false, otherwise it emits an error that says error user already voted. And then setting the user has voted, and then again setting the vote count. What happens here is that get user has voted is getting a Boolean value, and it takes basically the message sender object and some kind of key and makes the hash out of this. For set user has voted, it sets for the message sender basically a value of true, and then when it lets you only vote 1 time. Now, what are we going to do to deploy this? We don't have to redeploy our eternal storage smart contract because that keeps running under this address where it's already running. So we can access the same kind of variables, the same kind of data that is already running there. What we are going to do is we are going to redeploy our ballot smart contract. And if you're going to redeploy this, it gets a new address, but the storage is still the same. So if I hit get number of votes, it will still have the same count as up there. But now if I vote, I can vote 1 time. Let me make this here a little bit up. So you see I can vote 1 time. If I vote again, I cannot vote anymore. And that is the point what we are trying to make. We are trying to bring in upgradability while we keep maintaining the same storage as before. And it's perfectly possible with this pattern. One problem that you probably already see and think about is, well, we have still running the same instance over here that we had before, so we can still vote with the old smart contract. That is absolutely true. If you want to have this kind of thing in production, then you need some sort of pausing or stopping a smart contract logic that your smart contract is not reacting anymore on the old address, or you have some sort of in your storage smart contract, you have some sort of access control that only one specific smart contract address can access or can write values to the eternal storage pattern. Then you can stop using the old one, only use the new one, and therefore keep using the new version for your users. Again, our eternal storage contract over here is a simplified version of the one from Enela Petrova. So definitely check out the full version in her blog post. You can also find this on Ethereum-Blockchain-Developer.com in the upgradable smart contract section, a link to her blog post. And before we are going on, I want to talk a little bit about the pros and cons of using that. It sounds pretty good. There are some advantages and some disadvantages. The obvious advantage is it's relatively easy to understand. It doesn't involve any assembly magic. If you come from the traditional software development, these patterns should look fairly familiar to you. It would also work without any libraries over here, so you can just use the direct mapping between the storage variables that you need and your logic smart contracts. And there's a good reason for that, because the more simpler, the better it is usually. And well, it eliminates the storage migration after contract updates. One of the, which is a pro and a con at the same time, so I don't have really either a positive or a negative, is the address of the contracts change. This can be a good thing for transparency reasons, for compliance reasons, for legal reasons. It can be a bad thing if you have strong usability and user experience requirements, or if you have to update a lot of systems that use your smart contract address and maybe you don't have that all automated and so on. So it's just a fact that this has a new smart contract address if you deploy a new logic, but it is not really a bad thing. The not so good thing with this eternal storage pattern in particular is it has a quite difficult access pattern for variables. So while in a normal smart contract, you just have storage variables and you can do mappings of mappings, structs, and so on, you pretty much lose that ability over here with the standard eternal storage pattern. And the worst thing for me, it doesn't work out of the box with existing smart contracts like tokens, finished libraries that are out there that you can reuse for your convenience. You probably have to rewrite a lot of code that is already out there to make it work with eternal storage. And that is the thing that kind of breaks it for me if you want to start from scratch really quickly. But there are other patterns out there where you can keep your existing structure and so on and keep the address. So the next thing that I want to talk about is proxy patterns, and the first proxy from Nick Johnson. The first proxy contract that was ever proposed, at least to my best knowledge, came from Nick Johnson, and it's quite a while ago already. And if you don't know him, he is the founder and lead developer of the ENS, the Ethereum name service. Also make sure to check out his Twitter. He's quite active, quite funny what he's posting all the time. And he's always ahead of his time. Literally, he's from New Zealand, GMT +13. If you look at his code, which is over here that I've opened here, then you can see it's, well, first of all, it's pretty old already. It's 2016, and I believe it was written for Solidity 04 or maybe even earlier. It doesn't have any pragma lines. The whole thing just looks like from a previous version of Solidity, and quite a bit has changed. So in our remix over here, I have added a version, Solidity version 0.81 compatible first version of Proxy. So it's not his version anymore really, but it is still his version. I've just made it 3008 compatible. Okay, what about the structure that he has here? What is going on in his smart contract? Well, what basically happens is in a dispatcher, which is his proxy, you have a fallback function, and that fallback function uses a smart contract that is on a target address to, well, delegate a call. What is a delegate call? A delegate call is taking the logic that is running on a target address or on an address and executes it in the scope of the contract that calls it. So if the dispatcher is calling the target address, in this case example, and in example you're writing a value, then in that value will be stored inside the dispatcher, and the dispatcher will be the interface to the user. Okay, let's play around and you will see what happens here actually. The first thing is we need to deploy the example. That means our logic smart contract is running under this address. Then we are copying the address and we are going to deploy the dispatcher. We are going to paste the address from our logic smart contract. So I'm going to deploy this now. And now you see I have the dispatcher's functionality over here in the dispatcher, but what I want to actually have is the examples functionality over here at the dispatcher's address. And the way I do this, I take the dispatcher's address and I tell Remix my example smart contract is running on the same address that the dispatcher is running on. So now I'm going to have my interface from my example smart contract, but with the address of the dispatcher. And if I'm getting the uint, it's 0. If I set the uint to something, then it's going to update the uint, and the value is directly stored at the dispatcher's address. So even though I have an example smart contract running somewhere, the value here is 0 because it has a separate storage layout over here. Now that's pretty cool actually, especially because it was already proposed in 2016, and it's also pretty dangerous. But how does it work with upgrades? Now let's say in our example we found a bug and getUint should actually return 2 times the value for whatever reason. So we are going to update our I've updated our logic smart contract. We have to redeploy the logic smart contract. Now our logic smart contract runs on this address, and we are going to tell our dispatcher or our example smart contract, it wouldn't make any difference. We are going to tell our dispatcher to replace its logic smart contract that it has in his in his storage over here. We're going to replace the address with the logic smart contract with the new address. So what happens now is our interface stays exactly the same. We still have getUint and setUint, but our getUint will return 2 times the value. So if you're going to interact with this now, it has 2 times the value of the value that is stored in our uint, and that's still running on the same address that is our dispatcher's address, because the storage is stored there, and all it does is through the fallback function, if the dispatcher doesn't have the getUint and setUint values itself, it will hit the fallback function, and the fallback function will delegate the call to the address where the logic is stored, and that will execute getUint, and that will read out the uint value stored in the scope of the dispatcher. Now, obviously, there is a lot going on under the hood here, and this is not the end of the whole story, but it's the beginning of how proxies work internally. It has one large disadvantage, though, in my opinion, because your example smart contract needs to inherit the upgradable storage in order to have the storage pointers or the storage slots at the position where it needs to have them. If it doesn't have the storage, if it doesn't inherit the upgradable storage, it will get a storage collision. And to understand what storage collisions are, I've prepared a little example that I'm going to show you now. Now I want to talk about storage collisions, and I have an example here to make it clear what storage collisions are and why you have to avoid them. I have 2 smart contracts. I have one proxy that has pretty much the same fallback functions as the one that you saw before. It does a delegate call. That is the main point. It also gives you back the return data and so on. So it's a little bit more elaborate than the example from Nick Johnson, but under the hood, it does the exact same delegate call. Then I have a contract that I called lost storage. It stores an address and a uint. It looks like a very innocent smart contract. There's nothing specific going on up here. You just set the address and set the uint. In my proxy, I have one variable that is the other contract's address, which is our logic contract over here. Now I'm going to do the exact same thing as before. Let me clean here first. And I'm going to deploy our lost storage, which is our logic smart contract. Then I'm going to deploy our proxy clash smart contract, telling it where is our logic smart contract, which is our lost storage smart contract. And then I'm taking the address of our proxy smart contract and telling Remix that our logic smart that our lost storage smart contract is running on the proxy's address. Now the problem is that we have an address set here, even though we didn't set an address yet. So how is it possible? The problem is that inside Solidity, when it compiles these two different smart contracts, it will look at the storage variables that it has to store. So in our lost storage, it sees, well, there's an address. It will take a whole storage slot. And then there's an unsigned uint 256 that takes another storage slot. So this will start with storage slot 0, let's say, and this will start with storage slot 1. Then it deploys a proxy smart, or it compiles a proxy smart contract. It sees, well, it has one storage variable, that is an address, that we're gonna put on storage slot block 0. And now we are interacting with our lost storage contract in the scope of the proxy smart contract and read out the first storage block, which is the block 0. Because our address is stored on block 0, on storage slot 0. But in our proxy smart contract, that place is already used. So now we have our my address running or clashing with the proxy's address. And if we inherit different storage variables like we did in the previous example, then Solidity will know, well, there is a storage slot used. That actually doesn't use anything. There is a storage slot used. And over here is a storage slot used. So we have to have two different storage slots. The one starts with 0 and the other one with 1, and not both start with the storage slot 0 again. And there are ways around that. And if I would update my address now to some different address, then I completely lose the ability to interact with my smart contract. So now it's gone. There's nothing that I can interact anymore because our logic smart contract, or in our proxy, our logic smart contract points now to my own account, and you basically lost your logic smart contract. So let's talk about the real EIPs that are tackling with these problems. Let's start with EIP 897, the first real proxy. So the next thing that I want to talk about is EIP 897, ERC Delegate Proxy, and it was already created in 2018, so it's quite a while ago now. What does it do? It does pretty much the same thing that the example from Nick Johnson does, just in a little bit more standardized way, and we are not having any storage collisions. I've added the example over here in Remix, and you obviously can find it also in Ethereum-Blockchain-Developer.com in the Upgradable Smart Contract section, and I've updated it to Solidity 8081. What is the main point? We have a proxy storage that stores the logic, and then we have an actual storage smart contract that also inherits from proxy storage. So when we are compiling this, then Solidity knows that address goes to storage slot 0, that address goes to storage slot 1, that unsigned integer goes to storage slot 2. So it doesn't start both addresses from storage slot 0 again. Now, if you're going to compile this, then we obviously have to deploy the not lost storage first, then the proxy no more clash with the logic running on the no lost storage. And then we are going to tell Remix that we have our not lost storage running under the proxy's address. And then we can interact with it we see that my address is 0 initially, which it should be. And we are going to just set an address over here. And we can see we can keep interacting with our smart contract. And we also see that we actually have the address of the other smart contract, our logic smart contract, that points to the not lost storage smart contract in this address, but the storage is saved under the proxy. There's an obvious downside to that. If you are working with standardized smart contracts, then all the smart contracts that want to use the proxy, they need to inherit kind of a proxy storage, or at least know that it cannot start from storage storage slot 0. This brings me to the next EIP, which is EIP 1822, proxies without storage collisions and without a common storage contract. The next thing that I want to talk about is EIP 1822, the Universal Upgradable Proxy Standard. And this came on in 2019. It basically removes the need to inherit a proxy storage, and it's all described here and what it does. And that is the main point. It stores the contract logic on a specific storage slot, which is predefined, and not let Solidity choose the first storage block or slot from, well, the variables, how it's defined in the contract layout. And you can do this with sLoad and sStore. And you see here the proxy has an assembly line, and when the constructor is called, it gets the contract logic address and it stores it at a specific storage slot. And in this case, the storage slot is a Kazak hash of the word proxyable. And there is a very, very high chance that you will never have a storage collision with that hash here. And all it does then in the fallback function is it gets the contract logic that is stored first inside this specific storage slot. And the rest is the same as before. So I'm not going to explain this again, but let me run this example over here. Clean up first a little bit. Okay, we have our contract. Well, we have a contract which is a standard contract, and then I have a my final contract which I just inherit my contract, but this one would be like a standard token or any other contract that doesn't do anything with storage, anything with proxies, nothing. You can just have a normal standard ERC20 token contract and use that, and then I just use the my final contract because I want to have the proxyable interface as well when I'm dealing or when I'm deploying that. That's the whole thing. Okay, how are we going to deploy this whole thing? The first thing that you need to deploy is the my final contract, and then you get an address for that. But as you can see here, we have no real constructor over here. We have a function called constructor1. And you see in the proxy contract, it takes a constructor data field or variable, which uses it to actually call a function from your final contract to actually initialize the function. It can be called initializer, initialize, constructor 1, 2, 3, and so on. A function that is called upon contract initialization or deployment. And as you know, function identifier is the 4-byte value of the Kazak hash of the function signature. And that one would be, the function signature is constructor1. So if we have to get the first 4 bytes, then we have a web3.utils sha3 constructor1. And then we are taking the first 4 bytes, and that is the first 8 hex characters, with the 0x is the first 10. Oh, where is it gone? Nope. 010. Here we go. So that one would be the function identifier that we have in code for constructor1. So when we are going to deploy our my final contract first, then we get an address. And then when we deploy the proxy, then we have to give it the constructor data and the constructor logic constructor logic is the address where the constructor or where the contract runs, not constructor contract logic. And the constructor that we want to call is this one. So we are going to give it the function signature and transact. Now we have our proxy running, and the last thing that we have to do is we have to tell Remix, well, our final contract is actually running under the proxy's address. So now we have it over here, and we can see the owner, we can see our uint, we can increment a little bit. So you see it all works quite nicely. There are two important things to remember here. Number one is that this standard doesn't define a standard storage slot for this proxy or for the logic address. The problem with this is when you start to deploy your smart contracts, for auditors it's very hard, and for auditors it's okay because they are actually spending quite a lot of time with your smart contract. But if you're running something like Etherscan or Block Explorer and you want to give your users that are looking into smart contracts the ability to directly identify that this is a smart contract that can be upgraded and the logic is running under that address and those people are allowed to upgrade, then you need some sort of standards around that. And this is where the next standard comes in, EIP 1967. That is the standard proxy storage slots. And the other thing that is important to understand here is because of the way the storage layout works within Solidity, and it's also relevant for the other proxy smart contracts, you cannot change the order of the storage variables and you cannot remove storage variables. The reason is you stored here something on storage slot 0 and that is stored on storage slot 1. If you were to remove this and you recompile the smart contract, then Solidity automatically thinks this variable is now on storage slot 0. But because the storage slot 0 is already written in your proxy smart contract, you cannot do that unless you know that there's going to be severe side effects, maybe wanted behavior, but normally it's not. So how do we update this smart contract now? Let's say we have deployed the smart contract and we see, whoa, our increment function, that should actually be only called by the owner, but somebody forgot to uncomment this line. It's terrible. The functionality is broken. We have to update the smart contract. Very easy. You're just removing or updating your logic smart contract. You're going to redeploy your logic smart contract the same as before, and you're going to update the code to a new address. And you will see that the increment function can be called by the owner, but it cannot be called by anybody else anymore. Because we said in the constructor that we called through the init code here when we deployed the proxy, we said constructor data, go execute this constructor one function, and this constructor one function sets the owner, and our owner is the message sender, which was the person that executed the transaction. Okay, having said that, we are going to improve our smart contract now with standard proxy storage slots with EIP 1967. The next thing that I want to talk about is EIP 1967, standard proxy storage slots. And the idea behind it is really just to give the whole proxies standard slots so that it is easier for block explorers like Etherscan to go into these proxy contracts and extract the storage location of the actual logic contract implementation and overall make it a little bit more standardized. This EIP actually brings another advantage, which is beacon contracts. And the idea behind beacon contracts is that if you have multiple other contracts using the same logic contract, then instead of having multiple proxies with multiple times the same logic contract, you just have one beacon contract, and that is basically a proxy for proxies, so that when you update your logic contract, you don't have to upgrade multiple proxies at the same time. You just upgrade one beacon contract, and that's it. So this is the idea. I will not directly try it around, but I thought it is a good idea to show you the OpenZeppelin integration of this. And over here in the OpenZeppelin SDK repository, and what you can see here in packages, lib contracts, upgradability. You can find the link in the lab documents as well, so you don't have to type it in. And essentially the idea is that you have an upgradable proxy. And that upgradable proxy is going from base upgradable proxy. And in the constructor, all it does, it is setting the implementation logic and then doing a delegate call for calling something like a constructor, as we did in the previous example, where we have a function called constructor1. It can also be an initialization function, because when you deploy the smart contract, then the constructor gets called, but when you use it then in the actual implementation, then the constructor doesn't get called anymore. So you need some sort of other implementation function. So that is one of the few drawbacks that you have with using proxies actually. Okay, but you already see it is a kind of a more standardized storage slot. And when you have a look into base upgradability proxy, so let me go back, base upgradability proxy, then you see that one inherits from proxy. And it actually gives you the implementation back. So it loads from a specific implementation slot. That is a constant one. And it gives you upgraded to function, which upgrades the proxy to a new implementation. Okay, what do we have in the proxy itself? In the proxy itself, we have the actual fallback function, which is over here. So it's not called fallback, it's from Solidity 050. It's still called a no-name function, a function without a name. And that one calls a fallback, a function that's called fallback. So the fallback function calls a function that's called fallback. And that in turn will give you a little bit more flexibility in terms of having a layer between the actual delegate call and the will fallback. So in case you want to have, you want to catch specific functions that are not needed to fall back onto the logic contract, then you can do that here by inheriting this proxy contract. And then you have the actual delegate with the address of the implementation. And the delegate will do exactly the same again. It will go into a delegate call, take the result, and then either return it or revert. Okay, what is the point of doing that with standard storage slots? There is an implementation into block explorers like Etherscan that they can understand, or they can give the user the information that when the user interacts with a smart contract, that is actually a proxy contract and not an actual implementation contract. And the way they did that is when you're interacting with Etherscan, then you get a little drop down here, and then you have an is this a proxy functionality, and you can analyze if that is a proxy, and if the proxy's logic contract is actually also a verified contract on Etherscan. So I went to Etherscan and I took the next best contract that I found. Incidentally, it's a contract with 75,000 Ether on it, so it's a pretty expensive contract. I don't know what's running on there, but I went to the contract tab and then I went to more options. And you find this here, is this a proxy drop-down option? And I mean, it's already pretty clear that when you have admin upgradability proxy.sol, upgradability proxy.sol, and so on, you already know that this is a proxy. The question is the logic contract behind actually verified? So when you hit here and you see actually it's not verified, and you can get to the actual bytecode where the logic contract runs, then maybe something is off. But that's totally up to you. I don't know what this contract does. It is just for your information that you can actually go in to verify smart contracts where they are running. Okay, having said that, I would say we go on to the next one, which is the diamond storage and the transparent contract standard from NICMAJ. All right, there are two contracts that came from NICMAJ, and both are kind of having an interesting architecture. They are proxies, still proxies, but they have a slightly different idea behind. So I'm going to dive deep into the Diamond ERP 2535, but I want to briefly touch on the ERP 1538, which was withdrawn from him and was created 2018, end of 2018. And the idea is still to have the same kind of proxy contract that you have before, but with one fundamental difference, and that is instead of going through a full logic contract, we are going to assign actual function signatures, function calls, a specific logic contract. So with that in mind, you can actually detach, or you can, let's say, you don't have to deploy a full logic contract on a specific address. You can have multiple logic contracts on different addresses and just deploy specific functions from these smart contracts and bind them together into a proxy. So I think it's a pretty intelligent architecture, even though it's very hard to actually do that with Solidity, because you need basically all of the functions inside one of the Solidity files in order to let the Solidity compiler know what to interact with and what are the jump destinations for the assembly opcode. But I think the idea is still pretty good, that you can kind of modularize your code in specific ways that wasn't possible before. I think this architecture lets you actually create very large applications on the Ethereum blockchain without ever needing a second smart contract. So you can have one entrance smart contract that is your proxy, and then just from there you do your function calls if you have a clever function naming. Okay, this one was withdrawn, and the actual diamond storage is basically the same, just a little bit more clever. So I more want to touch on the diamond storage or on the diamond standard than on the transparent contract standard. So let me close this and let's talk about the EIP 2535, the diamonds. This was proposed and it's still in draft in beginning of 2020. And the idea really, and diamonds is a nice symbol, but the idea is really to have for each side of the diamond, you have function calls that are going somewhere else based on the function signature. So if you're going here into this fallback function, then you see the facet that is being called, or the logic contract that's being called, is coming from based on whatever is in the message signature, and that is the function signature from that should be called if it's not found in the actual proxy contract. So in that way, if there is one existing, so if it's not 0, then we're actually doing a delegate call into that and getting back the value to the user. And that is exactly the idea. All the functions that are necessary to actually add, replace, remove, or look into those function signatures are either called diamond cut to add, replace, or remove any of the functions, or the loop function to look into what is going on in the diamond standard or your diamond proxy. There is an example here, a library A with a struct, and that struct is basically your data structure to hold all the storage variables, which I'm actually not too fond of, but it's probably not possible any other way. And then a facet that uses the diamond storage on a specific storage location, which gets it back here, diamond storage, get back the diamond storage on a specific storage location. So it's again using the trick with specific storage slots and then getting that back and actually writing and reading from that struct here. So what you can see here is that the diamond smart contract, the proxy, actually maps the functions to the facets. So when you have a function and you know that the function signature is going to be E2532512, that might be get data or set data or get balance or transfer function, then it's going to be mapped to this facet. And the idea is that the diamond smart contract is going to map into the facets. And the facets it looks very much like a normal logic smart contract with the proxy, just that instead of only one, you have many of them. And then the storage is in a struct, and that struct is then on a specific storage location, and the facet is responsible for actually defining that storage location. And that lives inside the diamond smart contract. Very much the same like with unstructured storage proxies, where the storage is again in the proxy, and you just have a logic smart contract that is separate. I mean, this allows for quite an interesting way of separating code logic and storage. Obviously, you have the storage always in the Diamond proxy, in the main proxy, basically. But you can share different storage structs that are residing on a specific storage slot with different other facets. So if that is something that you need, that is something that your architecture has the necessity for, then definitely go with this one. Now, before I talk too much about theory here, I would say we just give it a try and see what is going on here if you're going to run that. Nick Mudge actually gave us a repository with all the code that is necessary, and he did free implementation of this. And as you can imagine, adding the different function signatures, mappings to the addresses, there's different ways to do that. And he implemented free ways of doing diamond cut functions. That is one with low complexity, medium gas costs, one with high complexity and low gas costs, and one with medium complexity and kind of high gas costs. And I will just dive into the first one to give it a try over here. So what I'm going to do next is I'm going to open up my Visual Studio Code and giving it a try locally in my, well, Ganache or whatever you have with Truffle. All right, I'm here in Visual Studio Code and I'm going to open up a new terminal, and I am going to clone this into this repository, into this folder. So I'm here in having the Diamond 1 folder. I have my contracts, facets, interfaces, libraries, and whatnot. And the first thing that I'm going to do is I'm just giving Truffle Test a try, because he gave us actually test cases, and I love test cases because they tell you how things are actually working. So when you go into the test case, then you see it's running a Diamond contract test, Diamond test for the contract. And what it does is, besides setting up something, it gets the function selectors, and then it is executing over here that you can add a test1 function. So it does a Diamond cut, and then it does the test function call. So that is kind of the important part for me, where it adds a function and does a function call. So why don't we just give this a try? Let me open up a second window over here with Ganache CLI. And let me just look into the Truffle config. If it connects to Ganache CLI, yes, it does, 8545 on localhost. So why not just type in Truffle test. Gotta go to the right directory. Now we can do Truffle test in the right directory. All right, and you can see the functions are getting executed, and you can dig into that easily. So what I really like to do is have a look at the main functions over here, what is going on. And now we're going to extract this knowledge that we have here and actually add a new facet that does, well, what does it do? Maybe just write some sample data. Okay, let me try and add a facet over here, and let's call this facet a.solidity. And of course, I have already something prepared. Let me walk you through the whole process. So again, we have a library, and again, it has a function diamond storage. And this one gets it back from the storage slot diamond.storage.lib_a. And so it always has the storage on a specific self-named storage slot that the other storage from the other facets, if there is any. What do we have? One libdiamond storage, so that it's not clashing with the storage. As you know, when we're running that through a proxy, then the storage will be used from the proxy's address. And when we are using the same storage slot, then we are overriding storage. So one thing that is extremely important here is that you keep a consistent naming schema Otherwise, you will run into the problem that you're overriding the storage from another one of your libraries or facets. That way you can also share storage if you want to. Okay, so we want to deploy the facet A into our Diamond smart contract or Diamond standard. And the way I'm going to do that is first you need a migration to actually deploy that, and then it's running under its own address. And then you need to tell your Diamond smart contract via a Diamond cut that it needs to add this set data A and get data A functions to the Diamond proxy. Okay, the first thing is we need a migrations file, and that is fairly simple. Let's call this free faceta.js, and we are going to deploy our facet A over here, and that will be deployed with this migration file. And then we are going to write a new test case, and that test case will add this facet A to our proxy, and then it should execute a function call. So let me do this here. Facet a.test.js. I like to do the test.js so VS Code actually knows what's going on here. And let me walk you through the code. So it gets all the functions that it needs over here, our Diamond proxy, our Diamond called facet, our loop facet to look into the smart contract, our ownership facet, and our actual facet A. And then it has some auxiliary functions to actually just make selectors available. It's like a reflection of the smart contract. And the actual thing happens over here. So inside this test case, it should add facet A function. So what does it do? It gets the address, or it gets actually the instance that is deployed through the migrations file. Then it extracts the selectors, and then it adds the facets A address into a wider array, so you can have multiple of facets from multiple smart contracts added at once to your proxy. I'm not doing that. I'm just doing one address at this Diamond cut here. And what it does is basically doing a Diamond cut on the smart contract's address from the Diamond smart contract and adding for the facet address with the add function for the Diamond, the selectors from our facet A. There's no initialization, and well, there's no initialization. That's it. And what it does next is it uses the loop to actually look if our smart contract, our proxy smart contract, has added on the address of the facet A the selectors that we try to add. So it's basically a read again. Okay, if we have those members, the next thing that we are going to do is we are telling our truffle that the facet A is running under the Diamond's address, which is the standard thing for a proxy, and we did that before. And then we use, a set data with some byte data, and in this case it's just 0xabcdef to store into the proxy, into the storage slot of our library. And then we're gonna read it out again and just make sure it's equal. Okay, so I stored that one. Let me save that one, and then let's run the test again. See what happens. All right, and as expected, it just runs through and it tells us, yep, we have the same members, and yep, we have stored and retrieved again some bytecode. Okay, now it is quite complex. I think it opens up new possibilities of storing or of interacting with smart contracts, especially larger ones. So if you are working on a very large project, then it might be interesting to look into how diamonds work, because you can have a consistent way of your users interacting with your smart contracts, and you can have a consistent way of upgrading them without touching too many other functions at once if you structure it correctly. That is the definitely a plus. The thing is, every smart contract in the system needs the adoption for the diamond storage, in my opinion. So simply adding an Open Zeppelin ERC20 or ERC77 token wouldn't be really advised. You have to adopt them for writing the diamond storage, or you have to be very careful because they start writing from storage slot 0, so you cannot interchange and interlink them. Also, sharing storage between facets is, in my opinion, pretty dangerous, and it puts a lot of liability onto the admin. So even though, with a lot of freedom comes a lot of responsibility, and over here it is a balancing act. I would very much maybe consider, if I have a larger team working on something, to structure it differently so that those storage sharing cannot happen. I also think that adding functions via the diamond cut is not as easy as it could be. It is definitely technically flawless, but from the usability side, the learning curve is pretty high, and it is absolutely nothing for beginners. What I also dislike is that you have to know in advance, or let's say the facets doesn't bring their own function definitions, and they don't bring their own configuration. So that, in my opinion, is a pretty large drawback. I know that there is a blog post. So there is one blog post from Hidden Tau that I found, which is doing this kind of architecture where the facet is actually bringing its own configuration to the proxy contract. And over here at the integrating into our platform part, there you see we also wanted to make doing upgrades as easy as possible. Specifically, each facet should be responsible for telling Diamond Cut which method it exposes. So the way they're doing this is by having the facet itself telling the Diamond Cut what kind of method it exposes, instead of going through this kind of reflection method for get selectors that tells you which selectors are available in this facet. Okay, now that is all that I actually wanted to cover for the diamond storage and diamond standard. I think those are two very interesting emerging patterns. I would recommend looking into them for very large projects. For smaller projects which maybe just need a common interface, a common address for the users, and then separate the logic into something else, the overhead might be too large. But I think it is extremely good to have those kind of standards emerging and have those options available. Now, having that said, I want to try something else. I want to dig into Metamorphosis smart contracts using Create 2. It comes with a grain of salt because this next option this next method that I want to discuss is actually only available until the self-destruct is going to be removed from the blockchain. There might be a protocol update coming in the future which removes the self-destruct, so then the next option isn't available anymore. And anyway, it's a very hacky method. It's not a standard. It is just another way of doing upgrades, and it should help you to understand where you can get scammed on the blockchain. And I would not recommend using the next method actually for your project. I would recommend knowing the next method, so when you're interacting with projects that you know what you're dealing with. Okay, let's get started with Metamorphosis smart contracts using Create 2. So far, all of the smart contracts are linking a proxy to another smart contract through the delegate call opcode. So the proxy address stays constant and all calls are forwarded from or executed in scope of the proxy. But what if there was a way to replace an actual smart contract altogether? It turns out there is actually a way to do that, and it's called Metamorphosis smart contracts. With this solution, you deploy a smart contract that itself deploys a smart contract. So you have a factory smart contract that deploys a smart contract, and that smart contract that you deploy, that replaces its own bytecode with another smart contract that runs on a different address. Now, it is going to be very, very low level here. It is kind of like super advanced stuff, and it might take a little bit of time to fully grasp the full details of what we're doing here. I will try my very best to go as detailed as possible on the underlying architecture. So the first thing that I want to start with is create two opcode primer, a little bit of an intro. And I want to get started with an actual code example of how create2 on the very basic level works before actually using create2 to then replace smart contracts with another bytecode and so on and so forth. So let's get started with create2 primer. Okay, how does create2 actually work? So let me give you a quick introduction. Create2 is an assembly opcode for Solidity to create a smart contract on a specific address. And create2 has a pretty cool advantage because the address is known in advance. Now, with the normal create opcode that you probably used, maybe without even knowing, when you deploy a smart contract, then the address is also known in advance because the address that the smart contract lives on is it's combined between the address of the deployer, so your address or the smart contract that deploys the other smart contract, and the nonce. And the nonce is an ever increasing number. So it's the transaction count on Ethereum. You start with 0, and every time you send a transaction, the nonce is increased. That's why when you deploy a smart contract with the normal create keyword or opcode, you cannot have an address 2 times where a smart contract lives on. You deploy it once, your nonce is maybe 1, and you redeploy the same smart contract with the same address, but with a new nonce because you cannot reuse your nonce. And your smart contract lives on a different address. Now, where comes create2? And that is the pretty cool thing. The create2 opcode doesn't have any nonces. With create2, you are using the deployer's address and the salt and the bytecode. And that's all there is actually to get the address of the smart contract that you're going to deploy. So when you have a smart contract that has a self-destruct function, then you can redeploy a smart contract on the same address where it was before. And normally you have to have the bytecode of the smart contract known in advance. And this should make sure actually that you can only deploy the same smart contract. But there is a very intelligent mechanism where you can replace, where a smart contract can replace its own bytecode. But we're getting ahead a little bit of us. And I just want to run through a quick example of how this address is actually calculated and doing a little factory smart contract where we are deploying another smart contract with the create2 opcode over here. All right. Let me walk you through the factory here. The factory is a simple smart contract that has one deploy function, which takes a salt. In this case, it's a uint and some bytecode. And what it does internally is it is going to take the data and the length of the bytecode and using the create2 keyword to then deploy the data with this specific size and the salt and get back an address, and that address is then emitted as an event. So how are we going to use that? We have to have some kind of smart contract that we want to deploy. So I already prepared something that I'm going to add right underneath. We have a smart contract without a constructor, and in this case we have one variable that is a public variable, and we automatically get a getter function for it. So what I'm going to do now is I'm going to deploy the no constructor smart contract with the help of the factory. And the way we're doing this is not like we do it with the proxies, where we tell the proxy where the data location of or the address of the logic contract is. We are going to take the bytecode of this smart contract and we are piping it through the deploy function. And how we're going to do this? Well, first of all, we need the bytecode. The bytecode is something you can find in the Solidity compiler plugin from Remix. And when you go down to compilation details, then you find over here the Web3 deploy section, and in here you find the data. And when I double click it, then it highlights everything, selects everything, and I can just copy. I also see that there is a copy bytecode function, but it doesn't do the same thing for me. So I'm preferring that one. Okay. Then we head over to the deploy and run transaction plugin, and we are going to deploy the factory. Now the factory is located at a specific address. And what we want to do next is we want to deploy the actual bytecode through the factory. So we give it a salt, let's say 1, and the actual bytecode. And then we hit transact. Now, when we inspect the transaction a little bit, then we see it emits an event. And the event is over here. And what it tells us is that our smart contract, our no constructor smart contract, now runs under this address. When I copy this address and I tell Remix that no constructor is located at this address, then we can see there's 5, the output of our public uint variable that we defined earlier. Now the cool thing is, because we know the salt, and the salt is something that we define, and we know the bytecode, with create2, we can actually determine the address where the smart contract will run in advance. So how are we going to do that? When you look at how the create2 keyword is defined, then you see it is the Kazakh hash of the deployer's address, well, some prefix and the deployer's address, a salt, and the hash of the bytecode. And from there, we take the last 12 bytes. Okay, so we can do that actually with web3.utils.sha3, which gives us the Kazakh hash. We need the factory address, which is the deployer's address, not our address, because the factory smart contract is deploying using the create2 opcode. We need the bytecode, and we need the salt. So why don't we use the console here from Remix to actually calculate our address that the smart contract will run under. So I'm going to do that with actual variables. So I have a factory address is this one. And I have the bytecode. Let me copy this again. Okay, and then I have the salt. So when I say factory address, then it should return me the address. That's great. So next thing is we need the web3.utils, and through the Remix console, we have the web3 object directly in our terminal here, .sha3. And from here, we need the prefix 0xff and then plus the factory address, but without the 0x at the beginning. So we slice it at the second position, plus our salt. But with our salt, it's a little bit complicated because we need to pad that correctly according to the Web3 ABI or the ABI encode parameter. And Web3 actually gives us a function to encode that according to the specifications. And that would be web3.eth.abi.encode parameter. And then you can say what kind of parameter is it, what kind of type is it. So we want to have it encoded as a uint 256. That's going to pad everything. And we want to encode the salt here. But again, it will give us 0x and then pad it with zeros like 0, 0, 0, 0, 0, and then 1. So we have to remove the 0x again. And then it's going to be slice 2. So we're going to remove the 0x at the beginning. And then we make it to a string just to be sure that it's going to be a string. And then we're taking the hashed bytecode. So again, web3.utils.sha3 and then the bytecode. And then again, we have to remove the 0x at the beginning, slice 2, and then make a string out of it. And then, well, let's execute this. That gives us some hash. And when you have a look at the address that we got returned over here, that is 0x71CO and so on. E68 at the end. So E68 at the end here is correct, and it starts somewhere over here. So we have to take the last part of that hash and then append a 0x before. So when we are using that functionality over here, then we have to add slice minus 40. So it takes the last 40 characters or the last 20 bytes. That's going to be this one. And when we are going to add a 0x at the beginning, then you get the actual address of the smart contract that was deployed using the create2 keyword. Now that alone doesn't help us very much, because as we know, the code, the bytecode that gets deployed must always be the same, because it's going to be a hash of the bytecode. So we cannot modify the bytecode. As soon as we modify the bytecode that we want to deploy, we get a different hash and then we get a different address. But we can do something else. We can actually use a bytecode that is going to be the same, always deployed, but it's going to call back into the factory, and it is going to ask the factory for a specific bytecode that is going to replace itself during the deployment phase in the constructor. And that is a pretty cool thing. Let me show you how that works. Before we are going to deploy that, let me walk you through the actual factory as it is now, because it's a little bit more complicated than before, but not a lot more. So we still have a factory smart contract, but this time we are not having a pure deploy functionality. We are having a functionality which already has a code that gets deployed, but this code will actually call back into the factory smart contract and ask the factory smart contract for an actual bytecode to replace itself. I didn't invent this bytecode piece myself. It's very short, but it does one thing very well. And if you have a look at the original implementation where it was suggested on a blog post, then I can walk you through the actual bytecode, what it does here. So I'm here at the repository from 0h and then /metamorphic, and I'm going to go to contracts, and I'm going into the Metamorphic contract factory. If you scroll down a little bit, then you find here the bytecode that I'm trying to deploy, and it has here the comments. So what it does is, that is pretty advanced already. It gets the program counter, it does some pushing under the stack, and what it does next is it gets a selector, which is the AAF10 selector, to actually call back into the smart contract, into the factory, to call a specific function, and that specific function is then called get implementation. So what it does is it gets the implementation and it expects back a bytecode, and thus exactly the Xcode copy, to then basically replace its own bytecode with the bytecode that is delivered by the factory from the, delivered to the Metamorphic contract by the factory. So the whole idea from the deploy functionality is that you again give it a salt and the bytecode, and the bytecode is going to be deployed using the normal create keyword or create opcode on a new address. So it's going to be the implementation contract. And then this implementation contract is going to be stored in the mapping. And in the mapping for the Metamorphic contract that we are going to deploy while using this bytecode and the salt. Now this Metamorphic contract gets deployed and calls back into the factory contract to get the address of the smart contract that we are going to try to deploy to the same address that is now running for the Metamorphic contract. I have prepared two test smart contracts here. I have a test 1 and a test 2. And what we're going to do now is we are going to deploy the test 1 contract, and then we are calling kill me. And then we are going to replace the test 1 contract with the test 2 contract running on the same address. I'm going to show you now how that works. Okay. I'm going to remove everything that I had before. I'm going to deploy my new factory. So my factory is running under this address now. And then I'm going to deploy my test 1 smart contract. So I go into the compilation details of my test 1 smart contract. Going to grab the bytecode over here. And I'm going to, with the salt of 1, place the bytecode using my Metamorphic contract onto a specific address. Okay, I'm getting back this address over here, and I'm telling Remix that my test 1 smart contract runs at this address. And you can see I have my interface of my smart contract set uint, so I can set my uint to whatever I want and get it back. So that works fine. I also have a kill me functionality that will kill the smart contract running under this address. So I'm going to use that now to kill the smart contract under this address. And now I can not interact with this anymore. So it's going to return me 0. I also wiped the storage. And then I'm going to deploy my test 2 smart contract. So I'm going to go ahead. I'm going to grab the bytecode from test 2. And I'm going to place the bytecode over here with the same salt, transact, and it's going to run under the same address as before, 0x7265 and so on. So what I can do next is I set uint, and what you see here, test 2 will set 2 times the uint. So I set my uint to 2 times. Well, this functionality doesn't really matter. What matters is that the bytecode from test 2 is clearly different than the bytecode from test 1, but it has still the same address. So it's very dangerous if you think of scenarios like where a token smart contract is running somewhere. You go in, you think like, oh wow, that's a really nice token smart contract. It gives me whatever percentage of staking, or it can be anything really, any project which first acts in your favor. And then you feel like, oh, well, that's very nice from the developers. They added a self-destruct functionality not to clutter the blockchain. That's a really nice behavior. They did a really good job. And what happens next is they're going to destroy the smart contract, and they're going to redeploy it with a different bytecode, potentially removing all the ETH that were there, changing the functionality so that it doesn't act in your favor anymore, and so on and so forth. So it's potentially pretty dangerous what happens here. And it's already pretty complex. One good thing is that the self-destruct keyword is probably going to be removed in one of the protocol updates from Ethereum. It didn't happen yet, and it's yet to decide if it's going to happen or not. But I would very much prefer that, because most of the smart contracts anyway don't use self-destruct, and it didn't really prove itself to be that valuable. All right, that's it for this example. And now let's do a quick recap of what happened within these videos. Now in this lab, you learn to use all the available methods to upgrade smart contracts. And from an audit perspective, it's usually always better to use simpler methods. I'm personally a big fan of keep it simple, stupid, KISS principle, although it sometimes means it doesn't look that elegant. If you want elegant solutions, then maybe you want to look into Diamond Storage or Diamond Standard, which is very interesting because it deconstructs a smart contract into smaller parts and then plugs them in back together using a proxy smart contract. I personally wouldn't choose this architecture at the moment because it adds a new layer of complexity to an ecosystem that is very often used to manage very large amounts of money. And if you manage very large amounts of money, then you want to have a simpler system, not a more complex system. Well, knowing what's happening under the hood, if I'd start a new larger project from scratch, I would probably use OpenZeppelin plugins now if upgradability is necessary to keep an address constant. If I don't need a constant address, I would probably just go with either eternal storage pattern or something even simpler. It's easier to audit, easier to get for other developers, and less error prone. Well, I hope this helped you to choose the right pattern for your project, and good luck. All right, now you are at the end of the video and you made it so far. Well, thank you for watching. If you liked the video, subscribe. I'm trying to do more of those. And if you have any other thoughts or comments, always welcome in the comment section, or just drop me a line, connect with me on LinkedIn. Or if you're in Vienna, well, let's have a coffee.